This video is just going to be a recap of what we did in class. These are the same slides from Wednesday, and we're looking at these three most basic position time graphs that we can start with. As a reminder, this is one-dimensional kinematics, motion in a straight line path. Kinematics is the study of motion without any concern for what's causing it, so we're not dealing with any forces yet. And we're one-dimensional, meaning one direction. We can go in two directions on that one line, one dimension. We can go forward or back. That's often represented as positive or negative. So, and the convention is to the right is usually positive if it's not stated, and the left negative. So we had these three basic graphs that we were looking to come up with when we were doing our dot diagram lab, dropping those clay spheres. And we have at first up top constant spacing, indicating that we have a constant velocity. Remember, our speed and velocity are not the same thing. Speed is a scalar kind of analog, similar to the vector velocity. And that velocity has a direction, and its magnitude may not be the same as the speed. It depends, okay? The only time it really can be the same is if we are doing one-dimensional motion and we're going in one direction. Then our speed and velocity can have the same magnitude. Okay, but we always have to make sure that velocity is displacement divided by change in time, whereas speed is just total distance divided by time. All right, the second graph there, or dot diagram rather, is the spacing increasing, so we said that's speeding up, and then the third one, the spacing decreasing, indicating it's slowing down, and then we have kind of a weird one at the end. We want to be able to analyze those weird ones, and also, as we'll see, in those interactives, if you're going through those already, then you see graphs and dot diagrams where the direction changes. Okay, so maybe of course speeding up, then it's slowing down, then it's reversing, and it stops, and then it goes forward again. We want to be able to look at that in terms of the dot diagram. That's like the most physical way to get an idea of what it is, what it means. Then translate that into position graph, position versus time graph. Remember, y-axis versus x-axis, so position's on the y, time is on the x. And then be able to change those position time graphs into velocity versus time graphs. And then change the velocity versus time graphs into the acceleration versus time graphs. So that each dot diagram, each single physical scenario can have its own position versus time graph, velocity versus time graph, and an acceleration versus time graph, all that describe the same physical scenario. So we should be able to produce any of those from the other. And we will have practice with that. This is the most basic one we got here, was our dot diagram with equal spacing, constant speed. So we can look at our change in position between each one. Our total displacement from t0 is from the beginning point. That's what we end up plotting when we have the origin down there as the 0 location of 0 seconds. So I just wrote that out for this one. These are the same slides from class. We're going to write out everything, and I'm going to skip ahead a little bit so we have everything plotted, and then my line of best fit right there for constant v. Okay, so that's when we have a linear graph with position time. That straight line, constant slope, indicates constant velocity. The slope on a position time graph indicates velocity. That is the velocity. So right now, my object is moving, is it moving in the positive direction or the negative direction? In the first quadrant here, y-axis positive upwards is increasing, so my x is increasing in the positive direction, so my displacement is positive, my velocity is positive, and I can tell my velocity is positive just by looking at that slope. Is it a positive slope or negative slope? It's a positive slope, it's a positive velocity. Okay? Our next one, we had spacing increasing, and that indicated a speeding up. I took a little more liberties in just writing out my differences here to kind of just get what I needed to plot the graph. So I had some erasures, let's keep going, and my line of best fit, there it is. So we notice in speeding up, we have a curve now in our position time graph. It's not straight, it can't be described by y equals mx plus v anymore, and that indicates that our velocity is changing. So we can see I've drawn the blue lines there to indicate the change in y on my graph. So we see there the slope is changing, and my slope is actually becoming greater and greater, more and more positive. So I'm traveling, this is still a position time graph, my position is increasing in the positive direction, so my object is traveling in the positive direction, and it's moving faster and faster in the positive direction. Its velocity is increasing in the positive direction. And I can visually see that as my slope increasing in its value. So I'll draw a red line here, a couple of them, just to indicate where the slope would be at different points. So I have a slope right here that's tangent, as best as I can make it on this iPad, to that point. That's the slope at some point down there where it touches the pink dot. And up here near the top, my slope is something like this. It should be tangent to that line, not cutting through it. And we'll say more about those tangent lines in the next video. But you can see the angle of my red line is different. That's supposed to be representing my slope. So you can see that change in that angle. It has become steeper slope. So the slope is my velocity on a position time graph. It's changing, meaning my velocity is not constant, and I can say it's becoming more positive because look at my slope. My red line is becoming more and more positive. All right, the last fundamental kind of basic one was our slowing down. There are my differences in my line of best fit. So now we have a slope that, let's look at what's happening to our slope. I start out with a slope like this. I'm going to try and get it closer to my line of best fit there, so it's about tangent. So there's my slope early on. My object's slowing down, and you can see over here where I'm about to draw my next. I'm just estimating the slope at a point, which you'll get to in calculus if you haven't already. There we go. So you can see the angle of my red line is getting closer to a zero angle. It's getting more and more flat, closer to a zero slope. And indeed, once I get to a zero slope, that indicates my velocity is zero. So here's a slowing down dot diagram and a position versus time graph that's indicating a slowing down. My slope is becoming less and less positive. It's approaching zero. And once I get to that perfectly flat zero slope, that'll indicate that we've stopped. And we saw what a stopped particle looks like in our next dot diagram and graph. There we got the 5 dots that I indicated, where the object's just sitting there, dropping oil drops. And this is the kind of graph we got. There was the first section of constant speed, so it's linear. The second section where the dots are all on top of each other, and look, zero slope, it's flat. Then I got that last section, part of it's curved because it's speeding up again, and then it goes at equal increments of 5 units of distance when it becomes a green line again there at the end. Here's an example of putting different pieces together. And it's good to be able to separate those out. We'll want to be able to separate the graphs into kind of distinct different parts that are easy to manage, and that usually means separating them out into triangles, rectangles, trapezoids. And then when we have the curve, like my orange part right there, that's usually when we want to be able to say, let's go use the calculus because it's a curved line. But we don't need to do that in here. We do need to just get the concepts. Okay, so let's see, do I have anything else I'm adding to this graph? Nope. This is the last one, so we want to be able to translate. Our goals here translate from the dot diagrams to the position time graphs. We're going to be looking at the velocity and the acceleration time graphs next class. Practice with the interactives on the physics classroom. There are 2 of them, matching the description of the dot diagram, then matching the dot diagrams to the graphs. Those are really good practice. If you can do those quick, you're on it. Okay? We want to be able to say what, for instance, this graph, I want to be able to eventually say, okay, now let's draw a velocity time graph of it, and then let's draw an acceleration time graph of it. So we'll end up with really 5 things all day. We'll have a dot diagram, we have a position time graph, we should have a velocity time graph, an acceleration time graph, and then the 5th thing will be that physical description using words, just saying what's happening to this object. We need to be able to hit all 5 of those on the nose every time we look at any one of them. Okay, the next video is going to talk about those velocity time and acceleration time graphs and how we look at the slope and the area in relation to those different types of graphs. Remember, I mentioned in class, I'm going to hit on it again. I have no titles on these graphs. Bad job. I should have position versus time. And it's kind of implied all of these were position versus time graphs. I do have my axes labeled though, so that should be clear. I got my units on each axis. I look at those units. And so, for instance, I got meters on the y, seconds on the x, so I know delta y, delta x, slope, that's meters per second. Easy way to remember. Okay? Look at those, work on the interactives on Physics Classroom, and we will continue on with graphing these, our position, velocity, and acceleration time graphs when we return next time. Keep an eye out for the next video.